Stanford University.
All right, shall we begin? Just to go back very briefly over what we said last week, what I said was that the best way to go about trying to estimate the rough parameters of the expanding universe is to begin with a model and then calculate its consequences. For what, I'll tell you in a moment. And if that doesn't work so well, adjust the parameters of the model and keep adjusting until you hit pay dirt and you agree with the data. You can do it the other way. You can take the data and try to run it backwards using the same equations, but it's often harder to do that. All right, the model that we put in basically consists of two things. It consists of a time history for the scale factor, A of t, and a specification of whether we're talking about a negatively curved, positively curved, or zero curved universe. Until we get to the properties of the cosmic microwave background and some of the detail that's contained in the cosmic microwave background, which we're coming to today, but until we get to those details, we really typically don't really see deep enough and far enough that the constant k, the positive curvature, negative curvature, or zero curvature, is really very critical to the analysis. It's like saying if you're on the surface of the Earth and you look out 1,000 miles, well, the curvature counts, but it really doesn't, it really is not that strong an effect. And if everything else that you're doing is not too precise, it's hard to tell whether the Earth is curved on a scale of 1,000 miles. Of course, if you have high precision, then you can tell. But all you're doing is looking out relatively nearby. The curvature doesn't matter too much. The same is true of negative curvature. And so counting galaxies, counting supernova, and things like that, which at not such large redshifts that never get bigger than 4 or 5, 6, 7, or something like that, you're not really terribly sensitive to the curvature. That's both good and bad. It's bad because it doesn't allow you to deduce from the counting of supernova and so forth with good precision what the curvature is, whether it's 0, plus or minus. On the other hand, since it doesn't matter too much, it means that you don't have to know too well what the curvature is to make conclusions about the other thing. And the other thing that counts is the curvature history, or the history of the scale factor, how it varies with time. So you start with a model which is scale factor as a function of time, and what you calculate, there's two things you can try to calculate. You can try to calculate the redshift as the intensity as a function of the redshift. In other words, what is the brightness of standard sources, standard candles, as a function of their redshift? That's roughly speaking calculating the Hubble law, relation between distance and velocity. And you can calculate from your model the number of objects that you see in the sky of a given redshift. In other words, the density of things out there is a function of redshift. And those are the two things which you can calculate from a model, compare with a model, and pin down your parameters as best you can. Just from the counting, you do not as well as if you knew the curvature with great precision, which takes CMB data to get at. But still, the tendency is toward a fairly flat universe, fairly flat, with no indication of either positive or negative curvature, consistent with zero curvature, and a expansion history which is consistent with the existence of a cosmological constant which contains about 70%, or dark energy, which contains about 70% of the energy in space. So that's what you learn from the counting of supernovae, or standard candles. It takes the other end of things, looking very, very deep, much deeper than where there are galaxies, or much deeper than where there are supernovae, or anything other recognizable standard candles, looking deep into the microwave background to do better. And so today we start to talk about the microwave background. Or more generally, what we want to talk about is the temperature history of the universe. The temperature history of the universe. Temperature, first of all, what is temperature? Temperature, you all know what temperature is. You put your hand on a hot flame and you know what heat is. It feels bad, it feels good, whatever your tastes are. But strictly speaking, temperature is a feature of thermal equilibrium. Thermal equilibrium is a condition for a system that is established after a period of time, basically by scattering. The kinds of systems we're thinking about are things made up out of particles. What particles? Well, what particles are present in the universe? There are photons, there are electrons, there are protons, and nuclei. If you get neutrons, they decay very quickly, but there are nuclei. And for our simple purposes, let's just say there are electrons, protons, and photons. Those are the particles that make up the universe today, at present times. And thermal equilibrium is what happens after you put particles together, allow them to collide with each other for a relatively long period of time. How long? Long by comparison with the time scales that it takes for actual collisions to take place. Particles collide with each other in microscopic amounts of time. They collide. There are mean free paths between particles. So there are various time scales. The time scales are not associated typically with the grand cosmological features of the universe. They're just associated with the nature of the gas, or the gas or fluid, or whatever it is we're talking about. The fluid might as well be here in the laboratory, and the various time scales have to do with the microscopic aspects of the fluid. And when the fluid sits around, well, I say fluid, I mean whatever it happens to be. I just use the term fluid because it can flow. The fluid, if left to itself for a period of time, will establish thermal equilibrium. It will establish thermal equilibrium as long as the expansion, whatever expansion might exist, as long as the expansion is much slower than these time scales for which these collisions taking place. Then it will establish thermal equilibrium. But you got to be careful about that. What causes things to become thermalized, or to become to thermal equilibrium? If I have a box, let's take as our model, our mythical box. Let's take our mythical box, and let's give it perfectly reflecting walls as usual, so that we don't have to worry about heating the walls, energy being absorbed by the walls, and so forth. Perfectly reflecting walls, and put photons into it. And let's put photons into it by shining a laser into the box. So we shine a laser into the box through a little hole. The radiation is in the box, and then we close up the hole, and the radiation bounces off the walls of the box. And if this is just pure photons with no interaction between them, and the interactions between photons is extremely weak, photons do not readily scatter off each other ordinarily, then the box will not come to thermal equilibrium. All that will happen is the pulse of radiation will bounce back and forth and back and forth and back and forth and back and forth forever and ever, almost forever and ever, without anything interesting happening. Well, maybe you consider that interesting, but without it, without the energy being spread through the system, without the energy becoming thermal. What it takes is some scattering. It takes some form of collisions to scatter the photons and cause the system to come to thermal equilibrium. Photons do scatter a little bit. There is some cross-section for the interaction of photons, but for photons of wavelength comparable to what we have in the universe today, the cross-section for scattering, or the probability for two photons to scattering, is so negligible that, that these photons would not equilibrate. They would not come to thermal equilibrium. What it takes to make things come to thermal equilibrium, to make photons come to thermal equilibrium, is some charged particles. Charged particles scatter very, very efficiently off radiation. An electron, a photon, or an electromagnetic wave goes past it. The electric field causes the electron to vibrate. The vibrating electron then sends off more radiation, and scattering is very efficient. If this box contained some density of electrons, let's call them E minus, minus for the fact that electrons have negative charge, if the box had some population of electrons in it, then scattering would be efficient, and the box would very quickly come to thermal equilibrium. Of course, it depends on what the distance between the electrons are, but you know, if we put a reasonable density of electrons in there, then photons scatter, electrons scatter, the electrons and the photons all come and form eventually a thermal soup, and under those circumstances, we would say that the box has a temperature. Now, the universe appears, there's good reason for this, but we're not going to get to it tonight. There's good reason for it, but the universe appears to be electrically neutral. There are not large lumps of positive charge and large lumps of negative charge in the universe, and certainly on the average, the universe appears to be electrically neutral. So it's not just electrons. In addition to electrons, there are protons and other atomic nuclei with positive charge. Let's simplify it and just say there are photons in the box. We'll call them gamma, gamma for gamma ray, but they're not necessarily gamma rays, just gamma for photon, and there are protons, P. That's what's in the box. Gamma, electrons, and protons. The number of electrons, let's call it N E minus, is the same as the number of protons, and that's why it's electrically neutral. Well, that's not why it's electrically neutral. The why of why it's electrically neutral is more complicated. It simply states that the box is electrically neutral. We, of course, use the fact that the charge of the electron is equal and opposite to the charge of a proton, another experimental fact that we're not trying to explain tonight. If the electrons and protons are freely moving in the box, in other words, if they're not bound to two situations, one situation that you could imagine is that the electrons and the protons are tied together into hydrogen nuclei. Hydrogen nuclei are electrically neutral. Electrically neutral objects are not efficient scatterers. it is true that they do scatter radiation a little bit, but on the whole, they're such weak scatterers that the very, very small dilute density of hydrogen in the universe today has so little effect on the photons moving through it that it would take forever, and I never even tried to calculate, but a very, very long time, much longer than the age of the universe, to cause the photons to come to thermal equilibrium. And so today, the universe is not in thermal equilibrium. It's not in thermal equilibrium. It doesn't have a proper temperature. Or another way of saying it is that the various kinds of particles are not in equilibrium with each other. The atomic nuclei that are out there, if you were to characterize them by a temperature, how do you characterize them by a temperature? Roughly speaking, the temperature is the kinetic energy of a particle. If you were to calculate them as, if you were to describe them as by having a temperature, the temperature would be much, much lower than the temperature that characterizes the photons out there. So the ordinary particles, electrons and protons, are not in equilibrium with the photons. There's simply not enough scattering for that to happen. On the other hand, if the electrons and protons were freely moving and not bound into atoms, then they would be efficient scatterers, and they would come to equilibrium together with the photons, and you would expect it to be characterized by a single temperature, the temperature of the electrons, the temperature of the protons, the temperature of the photons, all the same temperature, and in that circumstance, there's a well-defined notion of temperature. What does it take to make sure that the electrons don't fall into the protons and form atoms? Well, it takes a high enough temperature. When the temperature is high enough, the energies of the photons and the energies of the electrons and the energies of protons and so forth are large enough that enough collisions take place that they keep busting up the hydrogen atoms. There are some hydrogen atoms when the temperature is high, but there are also plenty of free electrons and free protons to scatter the radiation, and that maintains the thermal equilibrium. So if we're in the regime of temperatures where temperature is really meaningful, in other words, where things are thermal equilibrium, then the box of gas is described by a number of electrons and protons, or better yet, a density of electrons and protons, with the density of electrons and protons being equal, and a temperature, T, capital T. Okay. Now, the radiation in the box, every component of the radiation, every photon, if you like, or every bit of the radiation, is also characterized by a wavelength, lambda. There are many, many different wavelengths in the box. The box does not have a single wavelength once it's in thermal equilibrium, and the distribution of wavelengths is determined by the thermal properties of the box. We could also characterize radiation not just not by wavelength, but equivalently by frequency. And the relationship between frequency and wavelength is that the product of the frequency and the wavelength is equal to the speed of light. Okay, so either wavelength or frequency, and as I said, there are many, many different frequencies. There's a whole spectrum of frequencies inside the box. And it's characterized by a function. It's characterized by a function called the intensity I, and the intensity I is basically an energy density. It's basically an energy density, but it's a function of both the temperature and either the wavelength or the frequency. The wavelength or the frequency, and it's defined in such a way that if you multiply it by the volume of the box, or just a small little differential volume in the box, dV, and you multiply it by a small differential of frequency, d nu, that tells you how much energy is stored in the volume V in a band of frequencies between frequency nu and nu plus d nu. That's the meaning of the intensity. In other words, the energy density per unit frequency, and it's a function of the temperature. The higher the temperature, the higher the intensity. Now, we're not going to work through the theory of this intensity function, but we can actually work out the behavior of the intensity function as it would have been worked out before 1900. Before 1900, the only parameter, the only constant of nature which appeared in the theory of light and in the theory of radiation was the speed of light, c. So that's all there was c. And now you can use simple dimensional analysis to ask what must be the formula for the intensity as a function of t and nu, and you get an answer. Everybody know how to do dimensional analysis? You just say, all right, let me tell you how you do dimensional analysis. The first question is, what is the dimension of intensity? Well, it's energy per unit volume per unit frequency. What are the units of frequency, incidentally? Inverse time. Right. So whatever intensity is, it has units. Its units are energy per unit time energy per unit frequency, which means energy times time per unit volume. Now you can ask, what kind of quantity can you make? What kind of quantity can you make out of the temperature? Oh, the other question is, there's one other element. What about the temperature? What are the units of temperature? This is the units of intensity, energy times time over volume. What are the units of temperature? The units of temperature are basically units of energy. There's a historical glitch in the definition of temperature. Temperature was not originally defined. It wasn't even known that it was an energy. It was just defined in terms of boiling water and freezing water and dividing the gap into 100 little segments, and they were called degrees centigrade. But modern theories of what temperature is that temperature is just basically the energy of a molecule, the average energy of a molecule or a particle in a gas. Energy is temperature. Temperature is energy. The conversion factor, just the numerical conversion factor between energy units and conventional temperature units like centigrade, is a certain constant called Boltzmann's constant. So you'll often see formulas in which some energy or another, whatever it happens to be, is written as being proportional to some temperature times a constant K Boltzmann. The Boltzmann constant is, as I said, just a conversion factor. I'll keep it around, but for our real purposes, temperature is an energy and it has units of energy. Okay? And K Boltzmann is just some historical relic that we could easily set equal to 1 and not lose anything. I'll keep it around just because it's traditional to keep it around. Okay, so apart from this K Boltzmann, temperature has units of energy. And so we can ask what kind of dependence can I have, which has certain units, on temperature and frequency? Frequency has units of 1 over time. Temperature has units of energy. And I has to have units of energy times time over volume. It'll take you a few minutes. Just work it out. I'll tell you what the general formula has to be. It's of the form I equals temperature times frequency squared over the speed of light squared if we keep the speed of light in. That's the only thing around that we have is the temperature, the frequency, and the speed of light. And this is the only formula which has the right units. Of course, it's not the only formula that has the right units. There can be other formulas, like, for example, twice that. 2 has no units, and in fact, that's basically the right answer. Twice the temperature times the frequency squared over the speed of light squared. That's as, oh, not quite. I said I would keep K Boltzmann around, but the rule is always the same. Whenever you see a temperature in the formula, multiply it by K Boltzmann, and think of temperature times K Boltzmann as a single thing with units of energy. All right, so that's the formula for the energy per unit volume per unit frequency. Now, this formula is a disaster. This formula is a disaster. It was known to people in the 1890s, early parts of the, or late parts of the 19th century, that this was a disaster. If we plot this as a function of nu, we see that it grows parabolically. And therefore, the total amount of energy contained in this box is going to be infinite. There's just more and more and more energy per unit volume in higher and higher frequencies. All right, so you know the story, of course. The story was that a new constant was necessary. Oh, experimentally. And for the life of me, I have never been able to figure out how the experiments were really done to discover that any detail to this curve. I don't know how they were done because I don't know how physicists at that time could have measured the intensity as a function of wavelength. And I've looked it up, I've tried to find, I cannot, I don't know. I'm not even sure that they did do it, or we're just guessing about it. But this is the formula from classical physics. And of course, experimentally, the formula was quite different. It turned over and went back down to 0. So that the total energy contained in the box is finite. This fact, or the fiction that the energy in the box is infinite because of this formula, was called the ultraviolet catastrophe. And in order to have it turn over like that, it was necessary that this formula have another constant in it. This was the only formula that you could make that only involved the constant c. Necessary to have another constant, and that constant was, of course, Planck's constant. Adding Planck's constant into the formula, or adding Planck's constant, you can make up many formulas. But let me give you the right one. I'll give you the precise formula for I. And we'll see some interesting things about it. I is equal, this is the black body formula. This is the famous black body formula, or the Planck formula, twice Planck's constant. Anybody know what the units of Planck's constant are? Energy times time. Energy times time. Okay. Of course, what are the units of energy? You want to reduce everything to length, distance, time, and mass. mv squared. Mass, mv is length over time, mv squared. And mass times length squared over time squared. Yeah. And then to get h, you multiply by time, so it's m length squared over time. But whatever. definite units times nu cubed divided by c squared times a crazy function. And the crazy function was 1 divided by e, the Planck's constant times the frequency divided by kt. Again, that's K Boltzmann, goes together with the temperature as always, minus 1. All right, just to look at it, just for fun, what is it? Question? Okay. What does this formula have to do with this formula? Well, what the formulas are, the point is the formulas are the same for low energy, for low frequency. For low frequency, the exponential is an exponential of a small quantity here, when the frequency is very small. If the frequency is close to 0, you can expand out this exponential, and you use the fact that an exponential e to the x for small x is just 1 plus x. And then subtract off the 1, e to the x minus 1 is just x. So what's in the denominator here is just 1 over h nu divided by kt, but that means the kt can go in the numerator. That's what the complicated function is for small nu. And then if I multiply it by this, let's do it, twice h nu cubed over c squared. Notice, first of all, Planck's constant disappears. So in first approximation, for small nu, Planck's constant has canceled. 1 power of the frequency cancels. And if I didn't make a mistake in writing these things down, twice t kb, nu squared over c squared. I think I got it right. I think they agree. Okay? So now the point, of course, is that this becomes important when nu gets large. For small nu, the formula, as written by the classical physicists of the 19th century, Rayleigh, Jeans, and other people, that was correct. But as nu starts getting large, what happens to the exponential here? The exponential starts to get very big. So as nu becomes large, in particular, when h nu over kt starts to become bigger than 1, this exponential starts to get large. In fact, it becomes so large that the 1 isn't even important here. And this whole factor just becomes exponentially small. So there's a crossover point. There's a crossover point when h nu over kt is about equal to 1. Instead of this curve continuing up and up and up like a parabola, it rather suddenly turns over and goes exponentially to 0, thus solving the ultraviolet problem, the ultraviolet catastrophe. Now, this provides another interesting connection. It says that for every temperature, taking this formula, KT, not, I don't want to confuse time and temperature. This can be written in another way, incidentally. Let's write it another way. Instead of nu, let's remember that nu is equal to c over lambda. Nu equals c over lambda. We could plug that in here. And this says h c over lambda is bigger than 1. Did I get that right? Or that lambda is less than hc over kt. So high frequencies or small wavelengths are strongly affected by quantum mechanics, and the spectrum is driven very quickly to 0. There's a crossover point, The crossover point is exactly at lambda equals hc over kT. That's the crossover point. And more than that, that's where most of the power is. Most of the power, most of the energy density, or at least the largest part of it, is contained in wavelengths that are proportional to 1 over the temperature. That allows us to establish a connection, if you like, between lambda and temperature. Now we can sort of use that connection between lambda and temperature even when a system is not in strict thermal equilibrium, just to get a rough sense sometimes. If we know that we have a bunch of photons whose average wavelength is some particular wavelength, and we want to know how potent they are at doing various things to a system, we can, roughly speaking, replace it by the question of how potent would be radiation at a corresponding temperature. And so we could look at the photons that we see today, and from the bulk of the photons that we see in the universe, the overwhelming majority of them have a particular wavelength. The wavelength is about 1 millimeter. Okay? And that allows us to associate it with a temperature. And that temperature is about 3 degrees. We'll come back to that. But that does not say, and it's not interpreted, we should not interpret that in itself as saying anything is in thermal equilibrium. That's just a rough correspondence. It turns out to be much better than that, but for reasons we'll come to. Yeah?
Quick question. When Planck worked this out, was he working with a model of electrons and protons in that box?
No. Planck was doing a combination of two things. He was doing a combination of curve fitting. Okay, so various things were known. The fact that the wavelength, that the central wavelength here shifts with temperature, that was known, it's called Wien's displacement law. It's the displacement of the central peak as a function of temperature. Wien was a physicist of the 19th century, and Planck knew that very well, and he was able to read off the displacement law. He was able to read off a constant h. K was nothing new. Everybody knew that K and temperature go together by that time. Speed of light was known. And so the displacement law, which said that lambda goes as 1 over the temperature, was parametrized by a new constant called h. So the most important part of what Planck did was just to identify this constant, And this was, it's much deeper than it sounds. He also recognized that it had something to do with harmonic oscillators. He recognized, but he had the wrong idea. He didn't realize that it had to do with the radiation being described by oscillators. He thought that it had to do with the walls of the box containing harmonic oscillators of some sort, oscillating systems. It was before atoms were known for sure. Molecules were not really understood. But he had the idea there's something vibrating in the walls of the box, and the walls of the box are emitting, and he had some right ideas, some wrong ideas. It was Einstein, of course, who derived this formula in detail from a set of principles. But we're not, that's not where we're going today. Okay, so yeah.
The formula here up there, how does the units match up with what you put on the top? Energy times time divided by volume.
Okay, you really want to go through it, or you want to do it at home?
T times K Boltzmann is energy.
T times K Boltzmann is energy. Yeah.
So the rest of the units don't go in that.
Well, I don't know. If you want me to work it out, we can do it.
They work out.
Hmm?
H bar is energy time, C is lambda over time. It's energy
Yeah.
times the, it gives you lambda.
Thank you.
I think he's looking at the I and the units of I.
Yeah, the units of I.
So the units of I, let's see, the units of I are energy per unit volume per unit frequency. Or at least that's what they better be. Do I have it wrong? K times T is energy. All right, let's try it. Let's see what we get. Okay. I say I has units of energy divided by frequency, energy per unit frequency per unit volume. All right, and that is energy. What's the units of energy? What did we say energy was? Mass times length squared, mass times velocity squared. All right, mass times length squared over time squared. That's energy. What about frequency? Frequency is 1 over time. So that would put a time upstairs. And volume downstairs would be length cubed. All right, so let's see what we get. That's mass divided by length times time. Mass divided by length times time. Now we have to go over to the right-hand side. I probably made a mistake in substituting for the energy there since the energy already appears on this side, but let's do it anyway. That's the units of intensity. The units on the right-hand side are again energy. This is the right-hand side. Right-hand side. Energy, which is again mass times length squared over time squared. Frequency squared is 1 over time squared. This doesn't look like it's working out, does it? Oh, does it? Divided by c squared. C squared is length squared over time squared. So that's time squared over length squared. This doesn't look good, does it? What's going on? How much are we off by? Yeah, it looks like we're off by a factor of c. L squared cancels. Yeah, we're off by a factor of c somewheres. Length times time is length over time squared times time over length, which means a c. We're off by a factor of c. So is it upstairs or downstairs? I don't know what happened. C cubed on the bottom. Yeah. My guess is that the definition of intensity has an extra factor of c in it that I didn't know about because I remember this. Well, I may have remembered the formula wrong. I may have remembered the speed of light factor wrong. The speed of light, of course, is, yeah, okay, so what is the right formula? C cubed downstairs? C cubed downstairs, looks like. And now you can also ask about this exponential here. Is that dimensionless? It should be dimensionless because it has to be compared with 1, and that I'm sure is dimensionless. H nu, that's an energy. E equals h nu. Everybody knows that formula, right? Energy equals h nu, and kT is also an energy, so we're in good shape apart from that speed of light cubed, which I blew. All right, so in any way, that has no effect on this relationship between frequencies or wavelengths and temperatures. Given a temperature, this wavelength is called the thermal wavelength associated with that temperature. Now, there's something else helpful or simplifying about this formula. Let's just take the formula and get rid of everything that's irrelevant for my purposes right now. 2, h, and c are constants, so let me take them out of here and just say this is a proportionality. This is a proportionality. I is proportional to nu cubed times this thing over here. Notice that what's in over here is a function of nu divided by temperature. What's in here? It contains constants, k and h bar, but its dependence on nu, the frequency, is through the ratio of nu to temperature. Well, let's divide this by temperature cubed, and now multiply it by temperature cubed. What I'm interested in is the shape of the curve. The shape of the curve here, and for the moment, not the height of the curve. I'm interested for the moment only in the shape of this particular curve. And the shape of the curve, as a function of nu, is not influenced by whether I do or don't multiply by t cubed here. Multiplying by t cubed simply changes the overall normalization height of the curve, but it doesn't change its shape. Here is the thing which determines its universal shape, and notice that it's only a function of the ratio of nu to temperature. In other words, the shape of the curve, dropping the factor t cubed, is just a function of the ratio of nu to temperature. That means that if I change the temperature, all that happens is the curve rescales, the frequency rescales. For example, supposing I change the temperature by a factor of 2. What happens to this curve? It simply rescales by a factor of 2 along the nu axis here. All right, so I just stretch it by a factor of 2 if I want to change the temperature by a factor of 2. If I want to change the temperature by a factor of 100, I just stretch the curve by a factor of 100. In terms of wavelengths, I do the same thing. Remember that nu is proportional to 1 over the wavelength. We could write it this way if we wanted, 1 over the wavelength. If I change the temperature, then as a function of wavelength, I just squeeze the curve. All right, so there's a universal behavior to the shape of the black body spectrum. And if you know it at one temperature and you want to get it at another temperature, you simply rescale it. You rescale the frequency proportional to the rescaling of the temperature. And that's an important point. This is going to come up as a very important fact. And it's a simplifying fact. Okay. As I said, neutral atoms, and in fact today, most of the electrons and protons in the universe are bound up into atoms. And furthermore, they're very dilute. There aren't very many of them per unit volume. Many more photons than there are protons and neutron scatterers. And the scatterers aren't really available for scattering. They're bound up into these nuclei. And so the universe today is not in thermal equilibrium. The fact that there is a temperature associated with the black body radiation is a kind of accident, and we'll come to what that accident is. Okay, so when the temperature is too low in the box, the radiation decouples. The right term is that decouples from the charged particles. When the temperature is too low, the charged particles form atoms. The atoms are poor scatterers, and for the most part, the photons in the box, the radiation in the box, doesn't even see the charged particles. It just goes right past them and decouples from them. That's the right term. Now let's imagine starting with this box, and for whatever reason, let's suppose it starts at a high temperature. Let's suppose that it starts at a high temperature, so high that the electrons and protons in it are ionized, that they're not bound into atoms, or at least that not all of them are bound into atoms. And so it does have a temperature, it does have a thermal equilibrium, and the radiation spectrum looks like the black body radiation spectrum. Now let's start to expand the box. As we expand the box, just expand it physically, as we expand the box, it cools. It cools because the various particles do work on the box, and the work depletes the energy inside the box. The box cools, the temperature goes down, of course, and eventually it gets so cold in the box that the electrons and protons combine into atoms, and there just aren't enough sources of scattering. There aren't enough high-energy photons. There aren't enough oomph in there to ionize, to reionize the atoms. Okay. So what happens? The radiation decouples from the atoms. The atoms go their own way. Who knows what happens to them? Their temperature may also go down. The temperature of the radiation goes down, but it doesn't really stay in thermal equilibrium. To say it's in thermal equilibrium means the temperature of every part of the system is the same. So the system falls out of thermal equilibrium. At some point it falls out of thermal equilibrium, but nevertheless, as we continue to expand it, the shape of the black body spectrum here is sort of frozen in. It's frozen in for the simple reason that when you expand the size of the box, every single photon in it just has its wavelength stretched by the same factor. Every photon is stretched by the same factor, and as we saw, stretching the wavelengths by a factor of 2, for example, in this formula here is equivalent to just changing the temperature by a factor of 2. So as the box expands, every wavelength gets doubled, let's say. It mimics the effect of just lowering the temperature by a factor of 2, but only for the radiation. What happens to the other particles? Well, they do whatever they do, but they don't couple very much to the radiation. So in general, what will happen is the molecules, not the molecules, the atoms in there, will have a different temperature than the radiation. They won't come to thermal equilibrium because they're not efficient scatterers, but the radiation will have exactly the same form. The black body spectrum will not change except insofar as it rescales according to the change in volume or the change in linear dimension of the box. If the linear dimension of the box doubles, the effective temperature goes down by a factor of 2. If it quadruples, the effective temperature goes down by a factor of 4, and so forth. That's why today, when the universe is far too cold for it to be in thermal equilibrium radiation with matter, nevertheless, the spectrum of radiation in the universe has the black body form. Again, I emphasize, it's not because the radiation is in equilibrium with anything, it's just because it had this shape frozen in at some very early time and maintained that shape. Now, how do we know that it had that shape at a very early time? We know because we measure the shape of the black body spectrum, or we measure the shape of the photon spectrum in the universe. there's of course lots of different kinds of photons. There's gamma rays in the universe, there's ordinary light, starlight, and all that kind of stuff. But the overwhelming majority of photons are in the wavelength range of about 1 millimeter. Everything else is just more or less incidental, carries very little energy, and is fully accounted for by mechanisms that we understand. The dominant form of radiation, and I say that both by energy and by counting number of photons, the dominant form by a long shot is the blackbody microwave cosmic background radiation that was discovered in the 1960s. That radiation has been studied to death, and of course it does have the shape of a blackbody spectrum to very high precision. The error bars by now are very, very tiny. I'm not sure exactly how big they are, but they're so small that the deviations from the blackbody are much, much smaller than the error bars. Well, how can we know that they're smaller than the error bars? Well, because we have many, many different frequencies we study it at, and statistically, the curve fits the blackbody spectrum to a very high precision. So what we see today is a universe filled with radiation that appears, for all practical purposes, to be the remnant of a thermal distribution that must have become thermalized at a much higher temperature when the electrons and protons were ionized. That's, of course, our best guess as to what the thermal history of the universe was. But let's expand on it a little bit. What can we say? All right, first of all, what are the facts? What are the facts and what do we know?
Question.
Yeah.
A photon that travels in vacuum.
Supposing what?
A photon traveling under vacuum. How much space does it occupy?
How much space does a photon occupy? That is a loaded question. In some sense, the photon has no size at all, but it does have a quantum mechanical spread in its let's call it its probability distribution. Let's say it occupies a size roughly equal to its wavelength, to the inverse temperature. Yeah, I think that's the photons that are floating around not only have a wavelength of about this big, but the wave packets that describe them are also roughly about that big. Yeah, so a millimeter. A millimeter. Characteristic size scale of the photons, the wave packets, the wavelengths, all the same, about a millimeter in today's. Say it again? Yeah. But the peak here today is about 1 millimeter. Yeah. There's no universal, well-defined notion of how big a particle is. There's several different things that you could call the size of it. So I'm not gonna try to answer that. Okay. Yeah, there's another formula that I want to write down, which we'll come back to soon. Let's call this phenomenon where you go through the situation where you start with ionized gas, lower the temperature, and come out at the other side with lower temperature with atoms. Okay, that's the phenomena of combination. It's called recombination, but it's just combination, where the electrons and protons combine into atoms. That's the point at which the scattering stops. That's called decoupling, and it's characterized by a certain temperature. It's characterized by a temperature, and it's characterized by a wavelength through the connection between wavelengths and temperature. Okay, what about the wavelength of the radiation today? The wavelength of the radiation today, let's write a formula. It's a sort of trivial formula. The wavelength of the radiation that we see today, the remnant radiation from this black body spectrum, let's call it today. And now we mean the average wavelength. We mean the wavelength at the top of the peak. The wavelength today divided by the wavelength at decoupling. Is this bigger than 1 or smaller than 1? First question. Is it a big number or a small number? It's a big number. The waves got stretched, okay? What did they get stretched by? They got stretched by the expansion of the universe. So we can write that this is just the ratio of the scale factor today divided by the scale factor at the time that decoupling took place. The time that decoupling took place is not an absolutely rigorously, sharply defined time. It happened over some period of time, but the characteristic time that it happened over is relatively short, and so we can talk about the ratio of the scale factor. In other words, this ratio is the ratio by which the universe expanded over that period of time between the decoupling phenomenon and today. So it's interesting to ask, what do we know about it? Okay. It is also equal, since the wavelengths are inversely proportional to the characteristic temperature, it's also equal to the ratio of the temperature at decoupling to the temperature today. T today. Lambda today over lambda decoupling is T decoupling over T today. Okay? Whose temperature? Not the temperature in this room, not the temperature even in outer space if you are out there floating around. That would be mostly the temperature you would actually feel. Would probably have a lot more to do with the temperature of the molecules and atoms out there. No, we're talking about the temperature of the microwave radiation, the microwave background radiation. And this is the ratio of the temperature today to the temperature of, this today is about 3 degrees. 3 degrees centigrade, 3 degrees Kelvin. No. The temperature today is about 3 degrees. And it's an interesting question. What can we say about the temperature at decoupling? What was the temperature at which hydrogen recombined, or better yet, if you went in the other direction, what would be the temperature at which hydrogen would ionize? There's one simple answer to it. When the temperature is such that the photons have enough energy to ionize the atom. Okay? That's when the photon, anybody know what the energy of ionization of a hydrogen atom is? 13 electron volts. So if the photons, if the characteristic photons had an energy of 13 electron volts, then they would have plenty of energy to kick the hell out of the hydrogen atom and ionize it. That's a temperature of, let's see, that's a much bigger temperature than the decoupling temperature, and I'll tell you why in a moment. Okay, but that is one simple theory of the temperature of decoupling. It's the temperature at which the average photon has an energy comparable to the 13 point whatever it is electron volts that that'll ionize an atom. Okay, but there's another element, and the other element is that there's a lot of photons out there. The ratio of the number of photons to the number of protons is very large. In fact, the number of photons to the number of protons or the number of atoms or the number of electrons, they're the same thing, let's say the number of electrons, the ratio is about 10 to the 8th. Now, where did that number come from? How did so many photons get there? This is something we're going to try to talk about. How did it get to be? This is an observable fact. This is a fact that we know by looking at the matter in the universe. We know how many protons there are, or how many electrons there are, and we measure how many photons there are from the black body spectrum, and we know that the ratio of the number of photons to the number of electrons is about 10 to the 8th. Now, let's suppose that the temperature was just called T. Let's take the temperature T. What is the probability that a photon have a given energy? And the answer is, at a temperature T, the probability for photons to have different energies is of the form e to the minus, let's write it correctly, the energy of the photon, let's call it epsilon for the energy of the photon, divided by kT. This is a standard formula. This is the Boltzmann distribution, e to the minus energy over kT. This is the probability that the photon have an energy epsilon. Good, that's where we are. So now I can ask the question, what's the probability that a photon have the ionization energy? The ionization energy being 13.5 electron volts. Let's just substitute that in. Epsilon ionization. Epsilon stands for energy. Epsilon ionization is just good old 13.5 electron volts. That's the probability that a given photon have an energy which is big enough to ionize the hydrogen atom. If epsilon is very much smaller than kT, then this is a small, small number, exponentially small. On the other hand, there are a lot of photons. So instead of asking the question, what is the probability that any given photon have an energy big enough to ionize the atom, we could ask, how many photons are there that can ionize the atom? To answer that, we have to multiply this. In other words, per atom, how many photons are there that can do the job? And the answer is this number times 10 to the 8th. So in other words, we're actually operating in the tails of the distribution here. We have to multiply this by 10 to the 8th. And if this combination of numbers is order 1, is roughly 1 or bigger, then there are simply enough photons to ionize the electrons. Okay. There will be one photon. If this is of order 1, that says there will be roughly 1 photon per atom with enough juice to ionize it. All right, 10 to the 8th is approximately e to the 20, or something like that.
Is that at that energy or at and above?
At and above. Yeah, but don't forget, the spectrum falls off quickly, so it's mostly going to be pretty much in the vicinity of that energy. But yes, that energy or energy above.
Oh, question, would that 10 to the 8th be true way back when wouldn't that be a different number?
No. As far as the ratio of these numbers go, that was frozen in. There was no mechanism within this box for changing either the number of photons or the number of electrons or the number of protons, at least not until the temperatures are very, very much higher than we're talking about. The history back to decoupling is a history of pretty much conserved number of particles, conserved number of photons, conserved number of electrons, conserved number of protons, and to calculate that, it requires some calculation, but that's the bottom line, that the number of particles of any given species really didn't change very much. Okay, back to decoupling and probably well back before that. All right, so we have e to the 20 times e to the minus ionization energy over kT should be of order 1. And we can write that then that the ionization, E ionization over kT should be bigger than or equal to about, what, 20? 20. Or in other words, we can write this, turn it over. Let's turn it over. It says that kT is about 1/20th of the ionization energy. In other words, let me just spell out what this means. It means there are so many photons around that you don't actually have to heat the system up to the ionization temperature before there's a significant population of photons that can ionize the atoms. At a temperature 1/20th of the ionization temperature, there are enough photons around because of the large population of photons, it's 10 to the 8th. There are enough high-energy photons. High-energy photons now means above 13.5 electron volts. There are enough of them around to make sure that a significant population of the atoms are ionized. That happens when the temperature, when the characteristic temperature is only 1/20th of the ionization temperature.
How many degrees would that
You say
be?
the number of photons is constant.
What's
You say
that?
the number of photons coming out of the solar system is negligible, or
Yeah.
just that it's not enough ionization energy photons coming out?
No. The population of photons is very, very. The photons that came out of stars, they weren't even around at that time, so we don't care about them at all. And even if we did, the population of them is a tiny, tiny fraction of the population of overall photons. No, we're only counting the photons that are in the microwave background. In other words, the remnants or the relics of that early thermal equilibrium. Those are the ones that count as far as we're concerned. Okay, so we know now.
Question?
Yeah.
So at the time of decoupling, you got all these electrons and protons that combine with the hydrogen atoms and emit a 13.6 eV photon.
Say it again.
At the time of recombination there, the
Yeah.
electrons and positrons combine with the hydrogen atoms and emit 13.6 eV photons.
You mean when they recombine?
Yes.
Yes, we do.
So shouldn't there be a line in the spectrum of the black body radiation at 20 times the average energy?
Well, as long as the process is happening slowly enough, it will stay in thermal equilibrium. And if it stays in thermal equilibrium, the curve will be the right curve. If the expansion takes place a little faster, yeah, then there will be a kind of bump at the 13.5 electron volts. But as long as it happens slowly, the balance will maintain itself, and the population will conform to the thermal equilibrium. So technically, if the expansion is slow enough that the process is adiabatic, it will remain in thermal equilibrium at all times until the point where there simply aren't enough charged particles to keep it in equilibrium.
So what is that actual temperature in degrees?
Okay, that temperature is about 5,000 degrees, 4,000 degrees. 1/20th, you can plug in the ionization energy corresponds to a certain wavelength. The wavelength is some angstrom or whatever it is. You plug that in, you get an energy out, and the temperature at which the ionization happens or the recombination happens is about 1/20th of that because of the large population. And that brings it down to about 4,000 degrees. 4,000 degrees is much lower than the ionization temperature by what, 2 orders of magnitude? No, by a factor of 20. Right, right. 1.5, 1.25 magnitudes or whatever. Right.
I mean, Wolfram alpha says that 13.6 eV divided by 20 is about 7,891 degrees.
Okay, so it's 25. Where'd you get that number from? Say it again.
Wolfram alpha?
Yeah.
13.6 eV.
Wolfram alpha. What is alpha?
It's a program.
Oh, okay. Mm-hmm.
And it gives you twice that, essentially, almost 8,000 degrees. So it sounds like it needs to be a factor of 40.
It could be a factor of 40. Yeah, I mean, this is very rough. This is very rough. Yeah. Yeah, a detailed calculation has to be done. The detailed calculations have been done. I haven't done them. But this is the basic physics. The important thing is that it's a good deal lower than the ionization temperature by, if not a factor of 20, maybe a factor of 40. Yeah. Right. So recombination happens, or decoupling happens, at a temperature of 4,000 degrees. The temperature of the current radiation is 3 degrees. 4,000 degrees over 3 degrees is about 1,000. It's 1,200 or something like that. 1,300? Something like that, yeah. Okay, so that tells us then that the temperature at decoupling divided by the temperature today, putting everything together that we know, is about a factor of 1,000. But that's also the ratio of the scale factor. Remember, the temperature scales inversely with the scale factor. And so this is also equal to the scale factor today divided by the scale factor at decoupling. That's kind of an amazing piece of information to know that the universe expanded by a factor of 1,000 from the time that it was opaque. Opaque means that it was ionized and therefore light could not readily travel through it. All right, so that's one landmark, so to speak. That's one landmark going backward in time. Of course, there were a lot of landmarks going backward in time that I've overlooked in thinking about the history of the universe going backward. I haven't talked about galaxy formation. I haven't talked about black holes forming, all sorts of things. And we'll come back to those things. We don't have enough information yet to think about what it was that led the galaxies to form and so forth. But jumping back and ignoring that, we come to the first landmark, which is the decoupling landmark. Now, the second landmark in going backwards, the second important thing that happened in the sense of going backward, is the universe went from being matter-dominated to being radiation-dominated. Or to put it correctly, the universe went from being radiation-dominated to being matter-dominated. Remember what radiation-dominated and matter-dominated means? The equation of state for radiation and the equation of state for matter led to two different formulas for the energy density in the two kinds of energies. The energy density in matter scaled like some constant, let's call it rho naught, divided by the scale factor cubed. That's just the dilution of particles as the universe expands. Whereas rho radiation went like some other rho 1. I guess we could call this rho matter, rho radiation. It's just a number divided by a fourth. As we go forward in time, radiation becomes less important. Well, of course, it's less important today. It's much less important today. But as we go backward in time, we come to a time where this becomes bigger than that. Today, and for almost the entire observable period of the universe was matter-dominated, meaning that the matter contribution was much bigger than the radiation-dominated part. That affected the way the universe expanded. Expanded like t to the 2/3 instead of t to the 1/2 or whatever. But if we go back early enough, where the scale factor is small enough, we come to the point where there's a crossover between here and here. Let's see if we can estimate where that crossover happened, what the scale factors were when that happened. All right, first let's see what we know about the ratio today. Let's take the ratio today of, let's erase this formula, I don't want to confuse too many things here. Let's take the ratio today of the energy density in radiation to the energy density in matter. Okay, that's today. How do you do it? Well, first of all, you know from the black body spectrum, you know how much energy density is present in the form of photons. Basically, you can use the following facts, that for every proton, or for every hydrogen atom, there's 10 to the 8th photons. 10 to the 8th photons per proton. Second of all, we know the energy of each photon. The energy of each photon is about 10 to the -4 electron volts. That's the 3 degree, that's what corresponds to 3 degrees. Right? And what about the energy of a proton? The energy of a proton is 1 billion electron volts. 1 GeV, 1 billion electron volts. So there's a factor of 10 to the 8th, 10 to the -8th times, I guess, 10 to the 13th. 10 to the -8th is the ratio of the number of protons to the number of photons, and then 10 to the 13th is the ratio of the energy per photon, or per proton to the energy per photon. Anyway, it's straightforward to work out, and the answer is about 10 to the 5, 100,000. The ratio of matter to radiation today is about 10 to the 5. Okay, now, how did it behave in the past? In the past, as we extrapolate backward, rho matter scales with 3 powers of the scale factor, whereas rho radiation scales with 4 factors of the scale factor. That means the ratio here in time scaled like 1 factor of the scale factor. How far back? Oh, this is incorrect. Why is this incorrect? I made a mistake. I forgot about dark matter. Right, I forgot about dark matter. Dark matter has about 10 times as much mass as the ordinary luminous matter, protons, so this actually becomes 10 to the 6th. 10 to the 6th, ratio of rho matter to rho radiation. All right, now, the way that they scale as you go backward in time differs by 1 factor of the scale factor, and what that tells you is that in the past, at the time when the scale factor was 1,000,000 times smaller than it is today, that the energy density in matter and the energy density in radiation were the same. So as you go backward, when the scale factor is 1,000,000 times smaller than it is today, in other words, when the temperature is 1,000,000 times larger than the 3 degrees, That's well above, that's, what is it, roughly 1,000 times, that's 1,000 times the temperature of the decoupling period, when the temperature was another factor of 1,000 larger, universe another factor of 1,000 smaller. Then there was a crossover, and the universe became dominated by radiation. The radiation energy became larger than the matter energy. And as you go even further and further back, the universe becomes more and more radiation dominated. All right, so that tells us that if you go to the very early universe, that matter meaning massive particles, protons, electrons, but basically protons, nuclei, were very unimportant in the energy balance, and the Friedmann equation was basically just the equation coming from radiation. Right. Of course, that was very early, and we don't easily see directly back to that time. So in fact, we don't easily see back to a time when the universe was radiation dominated. Nevertheless, theory tells us that it must have been radiation dominated.
Wouldn't there be a temperature where even protons can't exist?
Yes.
That would change the equation.
We will come to that.
Okay.
Oh yes.
Okay.
Oh yes. Oh yes. Yes.
Yeah, I'm still confused. You said earlier that the number of that we have a constant number of electrons, protons, and photons, and to ignore all the stellar output today. You're talking about only the CMB, or you're talking about period, the whole universe?
No, the CMB.
Okay, CMB is where the constants apply. We do
Yeah.
get more photons.
Yeah. No, obviously, if we talk about starlight, the starlight is there today. It wasn't there at these very early times. Incidentally, all of these things are happening long before there were stars, and the temperature was way up there, long before there were stars, galaxies, and so forth. Yeah.
I have a slightly different way to answer the question that was asked earlier, which is if you take all of the free electrons, okay, and just deionize them all at the same time, you just add Ne to N gamma, and it will change by 1 part in 100 million. So it's sort of negligible.
Sorry.
If you just take N gamma over Ne and change it to N gamma plus Ne over Ne.
Well, we're going to come to that. Yes. Yeah, we're going to come to that ratio. That's an important ratio. We're going to come to it hopefully tonight. Okay, so we found two landmarks: decoupling.
Question. Sorry, when we were talking earlier, you said that the universe had expanded 1,000 times since the universe became transparent. Did that happen about 280,000 years after the Big Bang?
I can't remember if it's, that's the order of magnitude for sure. I can't remember if it's what's that? 380. Yeah, it's order of magnitude, a couple of 100,000 years, yeah.
The universe has only expanded 1,000 times in essentially 4 billion years.
In 13 point whatever it is billion years. Yeah, the time until the decoupling is negligible. It's a tiny time in cosmological scales. And then that's right, it expanded from what you normally think of as the Big Bang. It expanded by a factor of 1,000. The volume expanded by a factor of 1,000 times 1,000 is 1,000,000 times 1,000 is 1,000,000,000. Yeah. Yes, that's correct. That's the lesson, that over the period that we usually associate with after the Big Bang, the universe, it depends on what you define to be the Big Bang. If you define the Big Bang to be the decoupling era when the universe became transparent, then it expanded by a factor of 1,000. Now before that, it presumably expanded by a much bigger factor, and in fact, if we go back to the point where this crossover took place between radiation and matter, that's a factor of 1,000,000. Well, we can go back before that. We can go back earlier than that. The next important landmark, in fact, the next one that I can think of, is a landmark where the temperature was hot enough to create positrons.
Question.
Yes.
Do we know what A of 0 was?
What is?
A at time 0 was?
0.000.
No, we don't know what A at time 0 was.
And so if it wasn't 0,
Remember, yeah.
in particular,
Remember, I've warned you about this before. Space is pretty close to being flat. Okay? When space is flat, only ratios of A's have meaning. If you take a flat plane and you ask what the radius of curvature of it is, it doesn't mean anything. Its radius of curvature is infinite. But if the plane stretches by a factor of 2, so that the grid that's embedded in the plane stretches by a factor of 2, that's well defined. So to the extent that the universe is and was close to being flat, A doesn't really measure the radius of anything. It's ratios of A that measure the expansion factor.
that's what I was going to get to, is
Yeah.
so that at the time of the Big Bang, at that moment, the universe could have been infinite.
We don't know.
We don't know, but it
We
could have
don't
been,
know.
right? There's nothing, I mean, in my naive way, when I think of the Big Bang, I think of like this tiny universe, but I think that's probably the incorrect way to think about it.
I think that's an incorrect way to think about it. Yeah. Look, it depends on whether K is +1, -1, or 0. If K is +1, that means a closed and bounded universe, and A has some meaning. Now, still, the only thing we know is ratios of A. We don't know what the primordial size of the universe was when it first formed, if it was a sphere. If it is negatively curved, then it started out infinite. Started out as this infinite hyperbolic Escher drawing. So yes, so we're operating now at the level of what observational cosmologists can say, and what they can say is about ratios of A's. All right. Good. Let's keep going back in time. Yeah.
So when we get to the point of decoupling, is that where our observations end?
Yes. All right. Good. All right. Let's draw a picture in another. Yeah. That is correct. That's not necessarily where any observations can end. It's where our observations do end today. So let's discuss that a little bit. All right. So last time I drew a picture on the board. Time versus space. Time goes upward. Space goes horizontal. Let's imagine us sitting at the origin here. Here we are. Here's us now, later. And in fact, here's today. This line or this surface here represents today. And we look backward. We look backward along light rays. I mean, we see various things. Now, you asked me, repeat your question again now.
My question is, at the era of recombination,
Yeah.
that's kind of where our
Right.
cosmological
Yeah.
observations.
That's correct. That's correct. All right. So in looking back to different time periods, we see different distances. We can plot that by saying we sit at the center and we look out and we see 1,000 years ago, we see things 1,000 light years away, a shell. 1,000,000 years ago, or rather even further out, we see things as they were 1,000,000 years ago, further and further out, and eventually we see back, and looking out, we see back to the time at which this recombination took place. All right. That's actually looking at some time, but from our perspective, it's shells corresponding to different times. Now, we see light coming in from different places, and that's the subject of astronomy, of course. But before decoupling took place, the universe was ionized. Light does not, that's the whole point. Light scatters a great deal from ionized material. And in fact, the light simply didn't make its way very readily through the ionized material that was there before decoupling. That basically means, roughly speaking, that it was opaque, that the universe was optically opaque before decoupling. So that means we look out to a distance out here. That distance is what we're looking at when we're looking at the microwave background, basically. The telescopes that are looking at the microwave background are effectively looking back to there. And beyond that, they can't see because it's opaque. All right. Now, you might have a chance of seeing other kinds of things coming through that are less affected by whatever it is that's creating the opacity. For example, neutrinos. Neutrinos can pass through a lot more stuff. Low-energy neutrinos can pass through a lot more stuff than photons. And so, in principle, you can see neutrinos from further out. Gravitons even more so. So the distances to which you can see in principle may not be constrained to the same degree as the things that you can see by optical, I mean in the general sense, radiation, electromagnetic radiation. Electromagnetic radiation, the earliest that we can see to is the decoupling period. Right. Anything else beyond that is circumstantial evidence, shall we call it, but some of it we understand very well. Okay, let's keep going back in time, going out past here. Well, somewheres out here was the transition from radiation-dominated to radiation-dominated on this side, matter-dominated here. So there's radiation-dominated here, matter-dominated here. Here is decoupling, and then galaxies formed somewheres in here, and here we are today. So that's the picture of the universe in a nutshell. But more things can be traced back. We understand the laws of physics well enough to go to yet higher temperatures. It's an issue of going to higher and higher temperatures. Scale factor is getting, despite the fact that it looks like things are getting bigger as we go out here, the scale factor itself is getting smaller, which means the temperature is increasing. And something new happens when the temperature gets to be about 10 to the 10th Kelvin. That corresponds to A today over A of t of about 10 to the 14. In other words, at the point where the universe was 10 to the 14 times smaller, or where the scale factor was 10 to the 14th times smaller than it is today, the temperature would be 10 to the 14th times larger, and the characteristic photon wavelength, or the characteristic photon energy, would be about 1,000,000 electron volts. At this point, the characteristic energy of a photon is 1 MeV. So what I called epsilon earlier, the energy of a photon here is about 1 MeV. 1,000,000 electron volts. Now that happens to be about twice the mass of an electron, the mc squared of an electron. I'm sorry, it's about 0.5. Then it would correspond to the mass of an electron, Once the temperature gets up to that higher temperature, there are lots of photons around whose energy is high enough that if they collide, that when they collide, two photons have enough energy that when they collide, that they can make a transition to an electron E minus and a positively charged electron, a positron. In other words, pair production becomes possible. that whether it does or doesn't happen is a matter of quantum electrodynamics and computation, but it could not happen when the energies were much lower than the energy of the mass of an electron. So once you get up above this threshold here, the photons have enough energy that they can make electron-positron pairs, and they do. And they do. Quantum electrodynamics says that photons of such energy, when they collide, have a significant probability of creating an electron-positron pair. It's also true that electron-positron pairs will collide together and make pairs of photons. What happens is the electrons, positrons, and photons come into thermal equilibrium. The electrons and positrons, the number of electrons and positrons is no longer determined by memory of the future, memory of the future meaning today. When we go backward in time, we come to a point where new particles can legitimately be created by simply the energy of collision of photons. And the equilibrium, the number of such electrons and positrons, is determined not by history, but just by the temperature. And in fact, thermal equilibrium at that temperature, when you're at thermal equilibrium at that temperature, the number of electrons is equal to the number of positrons, not quite, we'll see in a moment, but close. Number of electrons is equal to the number of positrons is about equal to the number of photons. In other words, it's a soup consisting of electrons. What happens if the number of electrons and positrons gets too low? Well, they're replenished by collisions. Right? They're replenished by collisions, and the collisions will tend to simply resupply them. What happens if the number of electrons and positrons get too high? They will collide and make photons. So there's a balance, and the balance is not determined by anything except the temperature. And above that temperature, the three species of electrons, positrons, and photons are all about equally abundant.
Question.
Yeah.
So you said that the universe is electrically neutral, right? Mm-hmm. So you're talking here
Approximately. Yes, it is no, as far as we know, it's exactly electrically neutral.
So here you're talking about the creation of electrons and positrons that are beyond the actual electrons that are part of the universe now.
Well, of course, you can't tell which ones are which.
But this is just a balance. These are the additional.
These are the additional ones, right? And remember that this number is about 10 to the 8th times larger than the number of electrons today. Yeah, the implication of that is something like this. The number of electrons minus the number of positrons, that's the excess of electrons to positrons. That doesn't change. That doesn't change. The excess of electrons over positrons doesn't change as the universe cools. What does change is the sum of electrons and positrons. When a collision takes place, it creates an electron and a positron. Okay? So the electrons plus positrons increase, but the electrons minus positrons, in other words, the excess of electrons over positrons, does not change. So the number of electrons minus the number of positrons, that's basically today the number of electrons. Whatever the number of electrons today is, it was originally the number of electrons minus the number of positrons. And if you divide that by the number of electrons plus the number of positrons, well, the number of electrons plus the number of positrons is basically of the same order of magnitude as the number of photons. But the number of electrons today in ratio to the number of photons is 10 to the minus 8th. So this number is believed at the time when the universe was hot enough to create lots of electrons and positrons. This number is believed to have been about 10 to the minus 8th. In other words, if we forget about today and we just ask what was life like in the very, very early times when electrons and positrons were as abundant as photons, then basically for every 10 to the 8th electron-positron pairs, there was one excess electron. Now that's an extremely odd fact. That's an extremely odd fact, and it turns upside down the old question of why there are so many photons. The question is not why there are so many photons, as it is why there are so few, why the excess of electrons minus, why this difference is so much smaller than the total number of electrons and positrons. The question is not how did the number of photons get to be large. It's why is the excess of minus charges over plus charges so terribly tiny. But the question can even be turned around again by asking what is it that led to any difference between the number of electrons and the number of positrons. If the universe really started neutral, and for the moment suppose there were no protons, let's start with a world with no protons. Right? Start with a world with no protons. There's lots of photons, lots of electrons, and lots of positrons. And if you believe in symmetry, in particular symmetry between particles and antiparticles, you might guess that the way the world started was with an equal number of an equal abundance of electrons and positrons. If it had no electrons and positrons to begin with, it would very quickly, the photons would collide with each other, make electrons and positrons, but in equal numbers. So a natural expectation based on symmetry would be that the number of electrons and the number of positrons were equal. Plenty of, and that this would be 0. That turns the question around again. Given that the number of electrons and positrons are not equal, which is odd in itself, the question then becomes, why is it so small? But on the other hand, you could say, well, 10 to the minus 8th is a lot bigger than 0. So why is it so big? Why is it so big? Why is it so small? What is the theory which tells us why there's an electron-positron imbalance? Before we address that, let's go back, let's go even a little, we'll address that next time. That's the theory of particle, antiparticle excess of particles over antiparticles. Let's just go a little bit further back, another factor of 100 or 200 or 300 in temperature, and something else begins to happen. If we go back another factor of, let's say, certainly by a factor of 1,000, then probably a good deal less than that, then the photon collisions can make quarks and antiquarks. By the time it's 1,000 times hotter, the collisions can make protons and antiprotons. So if we go back another factor of 1,000, the universe should be filled with protons and antiprotons, again in equal abundance. The trouble is it's too hot for protons and antiprotons to exist. They simply, the same way that hydrogen dissociates into electrons and protons, the protons and neutrons, or the protons in particular, will dissociate into quarks. So above, what would it be? I lost track of the temperature, but another factor of 10 to the 2 or 10 to the 3, and the world is a hot soup of electrons, positrons, photons, quarks, and antiquarks. And am I missing anything? Dark matter, yep. Dark matter, which we don't know exactly what it is. Gluons, all sorts of things. And the population gets more and more complicated. But this little,
What about dark energy? How does that fit into the?
that is not important in the early universe. That's not very important in the early universe, so it's not part of the story at this stage. But what is true is that there are some relics. Some relics, like dinosaur hunting. What are the things which didn't change since the very earliest times? And it's expected or thought that the excess of matter to antimatter, in particular electrons to positrons, goes way, way back. Same with the number of quarks to antiquarks. Number of quarks, there are more quarks today than there are antiquarks. That's because there are protons and no antiprotons, or not many antiprotons out there. And so there's an excess of quarks over antiquarks. There's an excess of electrons over positrons. And the question is, what is the origin of that excess and why is it so small? What is the theory that accounts for it?
Are those similar numbers?
What's it?
Are they similar to 10 to the 8?
Those two differences.
Oh, they're the same. They're a factor of 3 because 3 quarks to a proton. But yeah, the excess of baryon matter to antibaryon, which means quarks to antiquarks, is the same as the excess of electrons to positrons. That's to keep electrical neutrality. Yeah. And so that's about the same number, roughly the same number. And, we can ask what in our experience with physics would could account for that imbalance. And we do have a theory of it. Not a detailed theory of it. That number 10 to the minus 8 has never been calculated as a hard number, but there is a rough theory of it, and we more or less understand why it's small. Yeah?
Where do the forces start coming together?
Well, I'm not sure what that means. The forces
In
do
other
what?
words, a combination of forces when you get back to high enough temperatures, the nuke forces and all the other forces kind of combine.
Oh, that's way back. That's way back. That's much, much hotter than this. Yeah, yeah. But let's just think about for a moment, starting with this condition where there's lots of electrons and positrons, lots of photons. It makes this hot soup. It's almost completely balanced between electrons and positrons with a tiny excess. And let's follow it forward in time. As we follow it forward in time, and it starts to cool down, the electrons and positrons will annihilate into photons, but typically the photons will not have enough energy to collide and make electrons and positrons again. So as you cool it down, annihilation becomes the dominant thing that happens, annihilation of electrons and positrons. And the electrons and positrons just annihilate. They just disappear and turn into photons. The photons scatter. When they scatter, they thermalize, and their temperature comes below the temperature needed to make electrons and positrons. And so if the number of electrons and positrons were equal, what would simply happen is essentially all the electrons and positrons would annihilate, and there would be none left, or almost none left. Okay? What we see is the leftover because it wasn't exactly balanced. What we see is the imbalance, and as far as we can tell, electrons dominate over positrons everywhere in the universe. It's not as if we were just a local pocket where there's more electrons than positrons, a statistical fluctuation. No matter how far out we look, what we see appears to be due to electrons and not to positrons. We see cosmic rays coming in. Cosmic rays appear to be made, and the cosmic rays, the highest energy ones, are cosmic in origin, very, very far away. Nobody has ever seen an anti-nucleus come in cosmic rays. There are a few antiprotons that come in, but that's easy to explain. If a high-energy particle comes in and hits the atmosphere, it will make some antiprotons, but the chances of it making an anti-nucleus, a whole helium nucleus, That's extremely small. On the other hand, if there were galaxies out there that were anti-galaxies, then we should see coming from them anti-nuclei, which would be of the same kind, or just the opposite kind, the opposite charge, of the nuclei that we see coming from ordinary matter galaxies. So the complete absence of anti-nuclei in cosmic rays are a pretty strong indication that everywhere throughout the universe, this sign difference here, or this excess of electrons over positrons, is the same, and of the same order of magnitude. In fact, it is of the same order of magnitude. So there's something to explain there.
Question?
Mm-hmm.
So that NE minus NE plus is also equal to N proton.
Mm-hmm. Mm-hmm.
Today.
Yeah. Well, at this time, the protons are still the same protons. Proton pair creation has not happened yet. So at this time, NE, this difference here is the same as the number of protons. Right. Right.
That was my question. What was the protons doing at this time?
At this time, the protons was pretty much just protons. They were knocking around. The temperature was high enough to kick them around a lot, but it wasn't high enough to destroy them. And it wasn't high enough to create new proton-antiproton pairs. Right. So there was a period when the protons were just plain old protons, and there was a tiny population of them compared to the photons, 10 to the minus 8th, and the proton number was about the same as the difference between electrons and positrons. Yeah. In fact, presumably exactly the same. Okay.
So you mentioned a couple times that what we see is probably a very small fraction of what there is.
Very likely.
So doesn't that make us doubt our results about the excess of matter over antimatter?
Mm-hmm.
And are there, I mean, so what do? You can't see in corners, not much you can do, but are there any alternative theories that perhaps make different assumptions about that imbalance, that perhaps are not imbalanced, but that we can't see far enough to tell?
What I can tell you is the imbalance is much too large to be a local statistical fluctuation. A local statistical fluctuation over a volume of, let's say, 10 to the 10th light years cubed, all of which had this same sign of imbalance, same order of magnitude, such a random statistical fluctuation of matter over antimatter would be violently unlikely. So the fact that the 10 billion light years or 20 billion light years or so that we see is all of the same sign certainly needs an explanation, and that explanation cannot be a random statistical fluctuation. But your point is correct. We simply can't see out beyond a certain distance, and if there's some kind of reason why there might be a transition to another region where everything is backward with respect to electrons and positrons, we wouldn't know it easily. So the answer is we don't have much information about what's out there beyond 15, 20 billion light years.
The cosmic microwave background, whatever it is, that the microwave radiation, which is
Let's call it by its current name, the CMB.
CMB. Okay. CMB is older even than the galaxies, is that correct?
Oh, it's older than galaxies.
And since we're receiving it, that means we're actually getting radiation from far enough back from before the galaxies.
Mm-hmm.
Does that suggest?
Yeah, galaxies formed in here somewhere.
Does that suggest that while we may not be able to see the entire universe, that it's unlikely that there's any galaxies that are so far away that they're receding from us fast enough that we can't see them, because they couldn't be further away than the source of the CMB, and we're still getting CMB signals, or am I not thinking about it?
This is decoupling. This is the time of decoupling over here. Here's today. We see back to here. That tells us absolutely nothing about whether there are galaxies up here or not today. This doesn't tell us anything. Right. We could not see them because we can't get light from them. From this great distance, we can't get light altogether. But certainly we can't get light from comparable times. So no, this tells us nothing about whether there are galaxies out beyond. What we do know is that by looking out as far as we can look, we see galaxies homogeneously distributed. No reason to think that there's a sharp edge of any kind in the galaxy population. They just look uniform. So most people would bet that that uniformity extends out beyond the distance that we can see through, C2. I would. Yeah. Okay.
For more, please visit us at stanford.edu.